Ehtesham-Ul-Haque? Ehtesham. Okay, sorry.
Hello. Hi everyone. I'm Ehtesham. I'm a third-year PhD student at Penn State. Happy to present our work, Abacus Gestures, a large set of math-based usable finger counting gestures for media interactions. My co-author and advisor is Syed Masum Billah. The family of media gesture is vast. It includes but not limited to finger pinching, traditional 10-finger counting, swapping fingers in different directions, making different shapes in midair, or using hand or finger to control an on-screen pointer. Each type of gesture has its limitations. Some gesture sets are limited in numbers, like traditional 10-finger counting supports only 10 gestures. Some gesture can be difficult to learn and memorize, like making shapes that are very similar to each other. Accurate detection may require additional hardware, like accurate detection may require additional hardware that may not be available everywhere. And finally, moving hand too much in midair can be fatigue-inducing and difficult to use. Our contribution is Abacus Gestures, which are midair finger counting gestures using classical finger abacus technique, also known as cheese and bob. Each gesture has an arithmetic representation starting from number 0 up to 99. On the right-hand side, you can see gesture 1, 2, 11, 23, and 99. These gestures take only These gestures take only 5 minutes to learn. Users can produce the gestures using the cheese and bob technique. These are made by opening and closing fingers, so the detection is very easy. Finally, a gesture can be made in multiple ways. It can be made in multiple ways, so that provides flexibility to the users. I will describe each of them in detail. First, I'll explain how different finger combinations are used to make abacus gestures. The finger abacus technique assigns certain oath to the 10 fingers of the hand. Here is the oath of the fingers in the open state. On the dominant hand, we have oath 5 for the thumb, and the other 4 fingers are oath 1 each. On the non-dominant hand, we have oath 50 for the thumb, and the other 4 fingers are oath 10 each. A gesture is the sum of the oath of the open fingers. So this gesture is the sum of the fingers oath, which sums up to 99. So this is gesture 99. In closed state, each finger is oath 0, so this abacus gesture is the sum of 10 zeros, which is 0. Detecting abacus gestures. I'm demonstrating how to make a series of abacus gestures representing 2-digit numbers, such as 44, 13, and 53. When I make a fist, that it transitions to the next number, and I can count until I can make a fist. Now I'm making gestures with the palm facing my body. Here I'm making thumbs up as a mnemonic, orienting my hand for detection. Now that we know how to make abacus gestures, let's try to make abacus gesture 26 by ourselves. So how do we do it? We make 10 with the non-dominant index finger, that's 10, plus the non-dominant middle finger, so 20. We take the dominant thumb, that's 25, plus another 1, that's the dominant index finger, that's 26. So this is 26. We have other ways to do this. This is not the only way. The other way can be the non-dominant index finger plus the non-dominant little finger, that's 20, plus the dominant thumb plus the dominant little finger, that's also 26. So there are multiple ways to do it. Now I'll present our gesture detection technique. In our current implementation, we used a 2D commodity camera like our webcam for capturing both hands. For extracting hand features, we used an off-the-shelf computer vision package, MediaPipe, which provides 21 key points for each hand, shown on the right side here. Each key point is the XYZ coordinate with respect to the top left corner of the frame. Based on the 21 key points, we developed an algorithm that is heuristic-based, rotation invariant, and highly accurate. Our heuristic is based on the tip and the midpoint for each fingers. Notice that when a finger is open, the tip is above the midpoint. When the finger is closed, the tip goes below the midpoint. We use this heuristic to distinguish between the open and closed state. To make our detection system rotation invariant, we used a hand-relative coordinate system with the wrist as the origin. I'll describe the coordinate transformation using these three figures. The initial coordinate system came from media pipe. Here the origin is at the top left corner, O. This is the X and the Y direction. First, we translate the origin from the point O to this wrist. So it comes here. Then we scale the Y-axis to point towards the direction of the fingers. And finally, we rotate the axis by theta so that the Y-axis passes through the wrist and the middle finger, and the x-axis is perpendicular to the Y-axis. So this is our final coordinate system. We evaluated Abacus gestures in 4 phases with 20 participants. At phase 1, we used a think aloud protocol where participants had to verbalize a strategy while making gestures. The second phase followed a Wizard of Oz protocol where we showed participants individual gestures without running the detection system and they had to make the gestures. Sorry. In the third phase, the end-to-end system evaluation, participants made a sequence of gestures with detection system enabled. The first 3 were conducted in the same session. After approximately 4 months, we sent out an online survey to all the participants, asking them the finger combinations for a set of gestures. For the interest of time, I'll only describe the result from phase 3. We found that the system could detect the Abacus gestures with over 98% accuracy. The gesture making time was 3.45 seconds in the first block and 2.38 seconds in the final block, which was 31.01% faster. The learning was significant between these 5 blocks. We also observed which gestures were easy or difficult for users to develop motor memory, which means raising fingers simultaneously without counting one by one. We found 5 categories: visual match, mnemonic, unimanual, bimanual symmetric, and bimanual asymmetric. For visually matched gestures, the gesture ID and the number of raised fingers are the same. Like Abacus gesture 1 needed 1 finger. All gestures were easy in this category. Mnemonics such as 5 as thumbs up or 99 as stop made this category easier to learn. Unimanual gestures had open fingers either in the dominant or non-dominant hand. Most of them are easy. Making 7 or 8 required counting explicitly. We grouped them as medium. Bimanual symmetric had same fingers in both hands, like 11, 77. They are grouped in either easy, medium, or hard. And the rest are bimanual asymmetric, where different fingers are raised in different hands. Although most of them are easy, some gestures like making 87 required focusing on both hands and consciously counting the fingers. I'll finish up with the use case and future work for Abacus gestures. This is one of the many ways someone can use Abacus gestures. In this example, we are showing a media text correction. You can see a paragraph with 55 words tagged with their indices. One of these words were formed at 23 as a typo. To select this word, user can directly make 23, and they use speech detection or other modality to correct this word. Finally, we observed that most of the finger-based media gestures can be represented with Abacus gestures. We have traditional 10-finger counting. These pin gestures are Abacus gesture 3. This can be 1 with a movement direction, and this is 1 or 9 with a projection of the pointer on the screen. We envision Abacus gesture as a superset of most, if not all, finger-based media gestures, and we try to adapt our framework as a general one that supports additional finger-based media gestures. In conclusion, we support Abacus gestures using Finger Abacus metaphor that supports 100 gestures. This can be learned very quickly, and we detected with 90% accuracy. We categorize the gestures that can be used for a large number of UI items for media interaction. Thank you, and I'm happy to take any questions.
Thanks a lot for an interesting idea. So again, one question. Okay, I think we have a chance to discuss and ask questions later on. So we now proceed to the next paper. We come back to sort of body tracking again, head tracking. So do we have the next author here? I think they're right here, right? And it's about tracking with millimeter radar. So it's